Okay, buckle up, because today we're diving headfirst into the mind-bending world of Einstein's relativity.
And we're going deep, folks, beyond the surface this time.
We asked you to send us your burning questions about relativity, and you delivered, pulling out some seriously fascinating excerpts from Einstein's own explanations.
Mhm.
And let me tell you, even Einstein knew how to break down complex ideas in a way that's surprisingly understandable.
It's really remarkable how he starts not by telling you what to think, but by challenging you to think differently about how we measure, well, anything.
Right, it's like we take for granted that a meter is a meter, but then Einstein comes along and asks you.
A meter compared to what?
Exactly.
Hmm.
And suddenly, the ruler itself becomes a mystery. I'd never thought about it that way before.
It's such a simple question, but it gets right to the heart of how we understand the universe.
And that simple question leads to one of the biggest mysteries that have scientists baffled before Einstein, the speed of light.
Yeah, we're used to speeds being relative, right? Like, a car seems faster if you're walking, but slower if you're on a train going the same direction.
Makes sense, right?
But light doesn't play by those rules.
Yeah, it's got a mind of its own,
It always travels at the same speed no matter what.
no matter how fast you're going.
Exactly. It's like the universe has a speed limit and light's always maxed out, like it's got a need for speed or something.
So if I'm on a spaceship going ridiculously fast, almost the speed of light, and I shine a flashlight ahead of me, the light coming out of that flashlight is still only traveling at the speed of light, even though I'm already moving super fast.
You got it. It's mind-boggling, right? Our everyday intuition tells us that light from the flashlight should be traveling at the speed of light plus the speed of the spaceship, but that's not how it works.
So it's not just that light is weird, it's that our whole understanding of speed breaks down when we're talking about light.
Precisely. And that's where Einstein's genius comes in. He realized that to make sense of this constant speed of light, we have to completely rethink our ideas of time and space.
Wait, so it's not just that light is weird, it's that our assumptions about time and space were wrong all along.
You're catching on. Einstein's theories of special and general relativity completely revolutionized our understanding of time and space. He showed that they're not fixed and absolute like we always thought, but intertwined and relative to the observer.
Okay, that's where I always get tripped up. Everyone says time is relative, but what does that actually mean in a way that makes sense?
Okay, so imagine two clocks, one here on Earth and one on a spaceship traveling at, say, half the speed of light.
Okay, I'm picturing it.
Now, according to Einstein's special relativity, the clock on that spaceship would actually tick slower.
Slower than the clock on Earth.
Exactly.
So time itself is passing at different rates for the two clocks. It's not just an illusion, it's a real difference.
That's the incredible part. It's a fundamental shift in how we understand time. And the faster the spaceship travels, the more pronounced this time dilation becomes.
So that classic thought experiment with the twins, one blasts off on a spaceship near the speed of light, comes back, and they've aged less than their twin who stayed on Earth. That's not just science fiction.
That's one of the mind-blowing consequences of special relativity, and it's theoretically possible.
Okay, that's special relativity. What about general relativity? It sounds even more intense.
Now we're getting to the really good stuff. General relativity is where Einstein brings gravity into the picture, but not as some simple force like we used to think. He showed that gravity is actually a warping of space and time itself.
Okay, I've heard that before, but what does it actually mean for space and time to be warped? Like, can you give me a visual?
Sure, imagine a bowling ball placed on a trampoline. What happens to the trampoline?
It dips, right? Like creates a dent in the fabric of the trampoline.
Exactly. Now think of that trampoline as the fabric of space-time. A massive object, like the sun, doesn't just exist in space-time, it actually warps the space-time around it, just like that bowling ball on the trampoline.
So other objects are affected by that warp, kind of like how smaller balls rolling on the trampoline would curve towards the bowling ball.
That's the idea. The closer you get to a massive object, the steeper the curve of space-time becomes, and the stronger the gravitational pull you experience.
So gravity isn't really a force pulling things down. It's more like things are just following the curves in space-time created by massive objects.
You've got it. That's the revolutionary idea behind general relativity. And get this. This warping doesn't just affect objects with mass, it affects everything that travels through space-time.
Wait, are you saying that even light bends?
Yes. Einstein predicted that light from distant stars would actually be bent as it passed by the sun, due to the sun's warping of space-time.
Hold on, how do you even prove that light bends? It's not like you can just see it curving in space.
You're right, it's not easy to observe. But during a solar eclipse in 1919, astronomers were able to measure the apparent positions of stars near the edge of the sun.
Uh,
And guess what? The stars appeared slightly out of position compared to where they should have been if their light had traveled in a straight line.
so the sun's gravity was acting like a lens, bending the starlight around it.
Exactly. It was a huge triumph for Einstein's theory.
That's incredible. But if gravity affects light, does that mean gravity affects time too?
Now you're really thinking like a relativist. And the answer is a resounding yes. But to understand how gravity messes with time, we'll need to dive a little deeper. And that's a story for part 2 of our deep dive.
Okay, so you're telling me light bends because of gravity. My brain is already starting to fry a little, but I need to know, how does gravity mess with time?
You're thinking like a true relativist. See, Einstein realized that time isn't immune to this warping of space-time. In fact, the stronger the gravity, the slower time itself passes.
Wait, are you serious? Time moves slower in stronger gravity. That's like some interstellar magic trick.
It sounds like magic, but it's backed by real science. Imagine you have two identical clocks, one sitting in a valley and the other on top of a mountain.
Okay, picture it, got it.
The clock in the valley, because it's closer to Earth's mass and experiencing slightly stronger gravity, will actually tick slower than the clock on the mountaintop.
So if I were to hang out in the valley long enough, I'd actually age a tiny bit slower than someone chilling on the mountain. Could I market this as an anti-aging treatment?
Well, not quite. The time difference is incredibly small, even with the difference in gravity between a mountain and a valley. But the effect is real, and it's actually been measured with incredibly precise atomic clocks.
Wow, so this isn't just theory. Scientists have actually seen time slowing down in stronger gravity.
They have, and get this time dilation effect isn't just some scientific curiosity, it has real-world implications.
Okay, like what?
Well, take GPS satellites, for example.
GPS.
They orbit Earth at a much higher altitude than we are on the surface, right?
Right.
So they experience slightly weaker gravity than we do down here.
So their clocks would run slightly faster than clocks on Earth.
Exactly. Now, this difference is incredibly small, but without accounting for it, those tiny errors would add up. And it would throw off GPS calculations completely. Your navigation system would be sending you all over the place.
Wait, are you telling me my GPS would be totally useless if it didn't account for Einstein's relativity? That's insane.
It's true. Your phone is a relativity machine.
That's wild.
And it all comes from understanding that gravity isn't a force acting through space, but that it is the very shape of space and time itself.
Okay, that's seriously profound. But you know what I find really fascinating? We've been talking about all this mind-bending physics, but Einstein also thought a lot about the meaning of it all, didn't he?
Absolutely. Einstein wasn't just a scientific genius. He was a deep thinker who grappled with the philosophical implications of his work.
So it wasn't all just like equations and experiments for him.
Not at all. He believed that a deep appreciation for the beauty and order of the universe could evoke a sense of awe and wonder that transcended traditional religious beliefs.
He actually called it a cosmic religious feeling.
Oh,
I
yeah,
love
that.
cosmic religious feeling. It's beautiful. But what did he actually mean by it?
For Einstein, it was about recognizing our place in this vast and awe-inspiring universe. It was about recognizing the incredible order and elegance of the laws of physics and feeling a sense of wonder and humility in the face of it all.
So it's not about a specific religion. It's more like feeling a sense of awe and connection to something much greater than ourselves.
Exactly. He felt this cosmic religious feeling was actually a powerful motivator for scientific inquiry.
Interesting.
It drives us to understand the universe better, not just out of curiosity, but out of a sense of reverence and appreciation for its beauty and complexity.
I love that. It makes me think, if gravity warps space-time and massive objects create these curves, what happens when something is incredibly massive, like a black hole?
Now you're talking about some of the most extreme environments in the universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their pull.
Oh, wow. Okay.
Once you cross a certain boundary, what we call the event horizon, you're not getting out.
So black holes are like what, cosmic vacuum cleaners sucking up everything around them?
They're often portrayed that way, but it's a bit of a misconception. It's not that they're actively sucking things in, it's that their gravity is so intense that anything getting too close, even light, gets trapped within this warped region of space-time and can't escape.
So if you get too close to a black hole, you're basically on a one-way trip to who knows where.
In essence, yes, once you cross the event horizon, there's no coming back. At least not with our current understanding of physics.
Okay, that's both terrifying and completely fascinating at the same time. And speaking of fascinating, one thing I always found mind-blowing is this idea that the universe isn't static, that it's actually expanding.
It's one of the most profound discoveries in cosmology, and it's a direct consequence of Einstein's theory of general relativity.
So how did we figure out the universe is expanding? Did Einstein just, like, do the math and say, yep, it's getting bigger every day?
It wasn't quite that simple. Einstein's equations showed that the universe couldn't be static. It had to be either expanding or contracting. But at the time, most scientists, including Einstein himself, believed in a static universe.
Wait, so even Einstein had a hard time accepting what his own theories were telling him?
It happens to the best of us. It wasn't until astronomers started observing the redshift of light from distant galaxies that the evidence for an expanding universe became overwhelming.
Okay, redshift, remind me what that is again.
Imagine the sound a car makes as it drives by. The pitch gets higher as it approaches, then lower as it moves away, right?
Right, right.
That's the Doppler effect, the stretching or compressing of waves as the source moves relative to you.
Right, like a cosmic ambulance siren.
Exactly. Light waves work the same way. When an object in space is moving away from us, its light waves get stretched, shifting towards the red end of the spectrum.
Okay.
And when astronomers observed distant galaxies, they found that almost all of them showed this redshift, indicating they were moving away from us.
So the farther away a galaxy is, the faster it's moving away from us.
You got it. It's like the universe is a baking loaf of raisin bread. And as the bread rises, all the raisins move further apart.
Okay, that's actually a really helpful analogy. So this expansion, it's still going on today.
It is. And not only is it expanding, but the expansion is also accelerating.
Oh, hold on. Accelerating. You mean the universe is expanding faster and faster all the time?
It's true. And this acceleration is driven by a mysterious force that we call dark energy.
Dark energy. Okay, that sounds kind of ominous. What do we know about it?
Not a lot, unfortunately. It seems to make up a huge chunk of the universe, though. Around 70% of its total energy density, in fact.
70%? That's insane. So most of the universe is made of something we barely understand.
Yeah, pretty much. But what we do know is that dark energy seems to be pushing everything in the universe apart.
So it's like a tug of war between gravity trying to pull everything together and dark energy pushing it all apart.
Exactly.
And right now, dark energy is winning.
Exactly. And because dark energy's influence grows stronger as the universe expands, this cosmic expansion is only going to get faster.
Okay, that's both mind-blowing and slightly terrifying at the same time. But I have to ask, if the universe keeps expanding like this, what happens to everything in it? What's the end game?
That's the billion-dollar question in cosmology. And while we don't have a definitive answer, there are a few intriguing possibilities. But before we get into the fate of the universe, let's take a look at one of the most famous equations of all time.
Okay, before we get lost in the ultimate fate of the universe, you mentioned something about a famous equation. I'm guessing it's not the Pythagorean theorem we're talking about here.
Not this time. This one's even more iconic, even if most people don't know what it actually means. I'm talking about E must equal.
EMC pi MCP. It's like the celebrity equation of physics, you know? Everyone's heard of it, but few actually understand it.
And yet it's surprisingly simple, at least on the surface. It basically says that energy, E, is equal to mass, m times the speed of light, c squared.
Right, but what does that actually mean for our understanding of, well, reality?
It means that mass and energy aren't separate entities like we used to think. They're actually different forms of the same thing, like two sides of the same coin. You can convert mass into energy. And believe it or not, you can even convert energy into mass.
Hold on. Are you saying that, like, a beam of light, which is pure energy, could theoretically be turned into something with mass? Like an object?
Exactly. It sounds crazy, like something out of science fiction, but it's true. The reason we don't see it happening all the time is because of that c in the equation, the speed of light. It's an incredibly huge number. So even a tiny bit of mass represents an absolute huge E amount of energy.
Okay, yeah. I'm starting to see why Einstein's ideas blew everyone's minds. So where do we actually see this mass-energy conversion happening in the real world? It's not like we can just, like, zap a flashlight and create matter, right?
Well, one dramatic example is in nuclear reactions, like the fission of uranium, for instance. A tiny, tiny amount of mass is lost when the uranium atom splits. But that tiny amount of mass converts into an enormous burst of energy, which is where nuclear power comes from.
So the next time I see my desk lamp, I should imagine it's not just giving off light, but it's technically losing a tiny, tiny bit of mass in the process, following Einstein's equation.
You got it. It's a truly mind-bending concept, but it's how the universe works. And it gets even weirder when we start thinking about the implications for the expanding universe.
Right. We left off with this whole dark energy is winning situation. What happens if the universe does keep expanding forever? Like, do we all just become, I don't know, cosmic dust, spread incredibly thin?
That's one possible scenario, often called the heat death of the universe, as the universe expands and cools. Eventually, even black holes will evaporate, stars will burn out, and everything will be so far apart that the universe becomes a cold, dark, and very, very lonely place.
Okay, yeah. That's pretty bleak. Any other less depressing options on the table?
Well, there's the big crunch scenario. That's where the expansion eventually slows down and reverses, pulling everything back together in a massive collapse. But honestly, based on current observations of how fast the expansion is accelerating, that scenario is looking less and less likely.
So we're back to the heat death. That's kind of a bummer ending to our deep dive, don't you think?
It might seem that way, but think of it this way. Even if the universe ends in a whimper or a bang billions of years from now, the fact that we're here, right now, able to understand even a fraction of its vastness and complexity, that's pretty remarkable in itself, isn't it?
That's a really good point. It's like Einstein said, the most incomprehensible thing about the universe is that it is comprehensible.
Exactly. And that sense of wonder, that drive to understand the universe around us, that's something worth holding on to, no matter what the future holds. Who knows what incredible discoveries await us out there?
You said it. So for anyone listening who's feeling their minds sufficiently blown by all this talk of relativity, black holes, and the fate of the universe, where can they go to learn more?
Well, Einstein himself actually wrote a book explaining relativity for a general audience. It's called simply Relativity, the Special and the General Theory. And it's surprisingly readable, even if you're not a physicist.
And of course, there are tons of amazing resources online too. Just searching for Einstein or relativity will lead you down a fascinating rabbit hole of articles, videos, and even interactive simulations.
The key is to never stop questioning, never stop exploring. As Einstein himself said, the important thing is not to stop questioning. Curiosity has its own reason for existing.
Wise words from a wise mind. And on that note, we'll have to wrap up our deep dive into Einstein's universe for today. It's been a wild ride through space, time, and the nature of reality itself.
Truly cosmic. Thanks for joining us on the journey.
Until next time,
Yeah.
keep those brains buzzing.